Our upcoming experiment in Chem 1211K is titled Demystifying Chemistry, Foundations and Nomenclature. And the essence of this experiment is to bring everyone up to a baseline of the foundational concepts and skills that you need to succeed in Chem 1211K lecture and laboratory. So we're going to be using primarily household or everyday products as a context to explore chemical nomenclature, the subatomic particles, molar mass and foundational concepts of stoichiometry, and other essential concepts of general chemistry that you'll need to succeed in this course. In the first part of the experiment, we're going to look at ionic compounds in a variety of different household products. And we're going to use the ingredient lists of these products to identify the names of these ionic compounds. So for example, we'll look at a bottle of toothpaste and see sodium fluoride as the active ingredient. From that chemical name, we can determine the chemical formula. In this particular case, it's NaF, one sodium cation for every fluoride anion within the structure. From that, we can derive the molar mass of the compound by considering the individual molar masses of the sodium and fluorine atoms within. And these are foundational skills that you're going to need to succeed in Chem 1211K. One of the products we'll look at in this part of the experiment is borax. And the chemical name of borax is sodium tetraborate decahydrate. This name is a little bit tricky to parse, particularly if you've never seen the tetraborate ion before and if you've never seen a compound name with waters of hydration within. So I wanted to spend a little bit of time on this to introduce these ideas. The chemical formula of sodium tetraborate decahydrate is given here. It's Na2B4O7.10H2O. And there are two things worth pointing out here. The first is the tetraborate anion, which you may not have seen before. It has the formula B4O7 2-. The negative 2 charge is counterbalanced by the positive 2 charges of the 2 sodium plus cations in this compound. The other thing you may not have seen is waters of hydration, and we see that in the name decahydrate. Waters of hydration are generally intact water molecules that are found within an ionic compound, most commonly coordinated to the cation, to the sodium cation in this case. And they're often written following a dot within the chemical formula like you see here. The deca prefix indicates that there are 10 waters of hydration within the formula of this ionic compound. And importantly, even though we're familiar with water as a liquid, the solid borax, the solid sodium tetraborate decahydrate, brings with it these waters of hydration, or contains within it the waters of hydration. So when we calculate the molar mass of this compound, for example, if we're making a solution or we want to know how many moles of the compound we've got in a given mass of material, we do want to include those waters of hydration when we do this. This is an idea that you'll use throughout Chem 1211K and 1212K laboratory courses because many of the solid compounds we'll work with will contain waters of hydration. In addition, we'll do some fundamental stoichiometry calculations with the mass of borax present in this household product. We'll determine the moles of oxygen atoms in total using the chemical formula, the molar mass, and the total mass of borax in the box. And from there, we'll use Avogadro's number, a key value in chemistry, to determine the number of oxygen atoms inside the box. In part B of the experiment, we'll focus on pharmaceutical products. And we'll see pharmaceutical products in two forms. Acetaminophen or Tylenol will be available as a solid. And given the chemical formula, we'll be able to determine its molar mass in grams per mole and use that to determine the number of moles of acetaminophen in a given bottle with a given total mass or in a single pill of a given total mass. We'll also look at ibuprofen, which is better known as Advil, as an aqueous solution. In other words, the active ingredient, the ibuprofen, is dissolved in water to create an aqueous solution. And solutions bring with them the interesting concept of concentration, how much ibuprofen in terms of moles is present in a liter or a particular volume of the solution. So the concentration of ibuprofen is given on the bottle, not in units of moles per liter, but in different units, typically mass per volume. And so we're going to convert from that mass per volume measure to moles per volume, or moles per liter. This is the most common unit of concentration that you'll use in Chem 1211K and 1212K. It's also known as molarity. In part C of the experiment, we'll dive inside the atoms in many of these household products and look at the subatomic particles within the atom and the idea of isotopes. You're probably familiar with the idea that atoms are made of protons, neutrons, and electrons. And different types of atoms have different numbers of these particles within them. And so in this part of the experiment, we'll look at a number of different atom names, such as nitrogen-14, and deduce from the name the number of protons, neutrons, and electrons within that atom. To do this, we start with the name of the atom, the element name. This tells us the number of protons, since the identity of an element is defined by its numbers of protons. In this example, nitrogen always has 7 protons. Every nitrogen atom has 7 protons. The number following the name, the element name, 14, is the mass number. And from this, we can deduce the number of protons in the nucleus, since the total mass number is the sum of the numbers of protons and neutrons. So 7 plus the number of neutrons equals 14. So the number of neutrons here is 7 in nitrogen-14. Given that this is a neutral atom, we can also deduce the number of electrons from the name, the element name, nitrogen. Since protons are positively charged and electrons are negatively charged, there must be 7 electrons within this neutral nitrogen-14 atom so that the charges of the protons and electrons balance and we end up with a neutral atom. The final part of the experiment focuses on the size of a mole and the question, how big is a mole? The answer to that question is, it depends, because a mole is just a number of things, a number of atoms or a number of molecules. So the size of a mole in terms of mass or volume depends on the size of the molecule of whatever substance or the atom of whatever substance we're looking at. So for example, a mole of iodine is much heavier than a mole of hydrogen atoms because iodine is a heavier atom than hydrogen, and a mole of each of those substances contains Avogadro's number of atoms. And so in this series here, from hydrogen to chlorine to bromine to iodine, the mass of one mole of the substance, or the molar mass of the substance, increases from left to right. So we'll look at the size of a mole for a number of different substances, and the prototypical substance we'll look at first is water. From the molecular formula of water, we can deduce the molar mass, the mass of a mole of this substance, by adding up the molar masses of the individual atoms within, and that will give us a value in grams per mole. If we want to know how big a mole of water is in terms of, say, volume, where we're trying to go is a number in, say, milliliters per mole. What's the volume per 1 mole of substance? And to make this conversion from grams per mole to milliliters per mole, what we need to do is multiply by milliliters per gram, the value of milliliters per gram for water. In other words, how many milliliters are there in 1 gram of the substance? If you look at that conversion factor, or that multiplication factor, you'll realize that this is just the inverse, or the reciprocal, of the density of water. Multiplying by the reciprocal of density converts the molar mass into what we call the molar volume, the volume of 1 mole. And once we have that number in hand, we're going to compare that to the volume of an everyday object of similar size. So it's up to you to come up with this. Once you have the value in hand, then start thinking through objects that have that approximate volume. You can even use the glassware in your lab drawers to get a feel for, how big really is 18 milliliters, for example, and start comparing to everyday objects. We're going to do this for a number of other substances as well. C6H14 is the colorless liquid hexane, and C2H6O is the colorless liquid ethanol. We'll also look at this for a couple of metals, aluminum, Al, and gold, Au. The size of a mole of these substances will differ substantially because the sizes, in particular the masses and the volumes of the individual molecules or atoms within the substances, vary substantially. And that's the essential point of this exercise, that even though a mole always corresponds to Avogadro's number of atoms or molecules, the actual concrete size of a mole in terms of mass or volume varies substantially depending on the submicroscopic or molecular structure of the substance we're looking at.